For clarification, you
I am
can
Dr.
refer
N.
the following
Prabavathi,
books.
Associate Professor and
That is,
Head,
The Advanced Quantum
Department of
Mechanics by
Physics,
Satya
Sri
Prakash.
Sharda College
The
for
another
Women,
book is
Autonomous, Salem,
A
60.
Textbook of Quantum Mechanics by Matthews and
In this
Venkateshan.
video,
Thank you very much.
let us see about the partial wave analysis. In the scattering process, a parallel beam of particles of given momentum is directed towards a target which deflects or scatters the particle in various directions. Eventually, at large distance from the target, their motion is directed radially outwards. It is useful and convenient to choose a coordinate system with the origin at the position of the target or at the scattering center, and with the z-axis as the direction of incident beam. The direction of the scattered particles is indicated by the polar angles theta and phi. The angle theta is called angle of scattering, which is nothing but the angle between the scattered and incident directions. These two directions together define the plane of scattering. The azimuthal angle phi specifies the orientation of this plane, that is the scattering plane, with respect to some reference plane. This figure clearly explains what I said previously, that is, this is the incident ray or incident particle along x direction, and here the target. When this incident particle allows to fall on a target, it gets scattered radially outward direction, and this ray is called scattered ray, and this cone is called cone of scattering. The scattering plane is nothing but a plane which consists of scattered ray and the incident ray, and theta is the scattering angle, and where phi is the azimuthal angle, which is the angle between the scattering plane and the reference plane. This reference plane contains z-axis. In the case of scattering, when the particle involved are quantum mechanical objects, we must describe them by a wave function. The wave function will be a stationary one if we assume that a steady incident beam is maintained for all time. The phenomena of scattering is manifested as a distortion in the stationary wave pattern caused by the presence of scattering center. At large distance from the scattering center, that is, when r tends to infinity, the form of the wave function u of r comma theta must consist of a part u incident corresponding to the parallel beam of incident particle and another part u scattered representing the scattered particle moving radially outward direction from the center. Therefore, u of r comma theta when r tends to infinity is made up of u incident and u scattered. We shall now analyze this requirement in more detail and thereby arrive at an expression for the scattering cross section in terms of asymptotic form of the wave function. The beam of the incident particle with momentum p along z direction must be described by the plane wave. Therefore, u incident is e power ikz. As far as the scattered particles are concerned, we shall assume that they have the same momentum as the incident one, that is, the scattering is elastic scattering. Then the wave u scattered representing them must have some propagation constant k, but it must be a spherical wave since these particles move radially outward. The only such waves are e power plus ikr and e power minus ikr. But the latter one, that is e power minus ikr, is an incoming wave, that is contracting towards the origin. Since the scattered particle moves outwards, we must choose the outgoing wave u scattered is directly proportional to e power ikr. At the same time, this u scattered is decreases as r increases. Therefore, there is 1 by r dependence, and f of theta pi is the proportionality constant. Therefore, u scattered is nothing but f of theta pi e power ikr divided by r. Thus, the form of u of r theta when r tends to infinity in the case of elastic scattering is given as in equation 2. The method of partial waves is mainly applicable to spherically symmetric potential and consists of expansion of wave function u of r comma theta in terms of angular momentum eigenfunction. The new expansion of u of r comma theta must be consistent with the asymptotic form. With this requirement imposed, one gets a formal expression for scattering amplitude as an infinite series. Each term of the series is the contribution to f of theta from a partial wave characterized by a particular angular momentum L. We shall now see that the first few terms in the series approximate f of theta pi if the incident particle is of low energy. Thus, the partial wave method leads to low energy approximation. Using Rayleigh's expansion for e power ikz, u of r comma theta can be expressed like this, that is summation over L I power L 2L plus 1 JL of kr PL of cos theta plus e power ikr divided by r f of theta. Here this f of theta is known as the scattering amplitude as we said previously, and this JL of kr is nothing but a spherical Bessel function. This JL of kr is sin kr minus L pi by 2 divided by kr. We substitute this in equation 3, thus we get equation 4. Then this sin kr minus L pi by 2 divided by kr can be written as e power I kr minus L pi by 2 minus e power minus I kr minus L pi by 2 divided by 2I kr. Thus we get Equation 5. Now, for a spherically symmetric potential, the Schrodinger equation is minus h cross square divided by 2 mu del square plus V of r into u of r is equal to E into u of r. This can be separated into radial and angular parts. The angular part of the solution is spherical harmonic YLM of theta pi, which crumbles to the legendary polynomial PL of cos theta under rotational symmetry. Therefore, the solution of the Schrodinger equation can be written as the product of the radial wave function and the legendary polynomial. Therefore, the solution of equation 6 is given as u of r theta is equal to summation over L I power L 2L plus 1 RL of r PL of cos theta, where RL of r is the solution of the radial part of the Schrodinger equation. In the field free case, that is when V of r equal to 0, the solution to the Schrodinger radial equation is JL of kr or eta L of kr. In particular, if V of r equal to 0, the only admissible solution is JL of kr, because eta L of kr becomes infinite at r is equal to 0. For large values of r, the asymptotic solution will be the linear combination of JL of kr and eta L of kr and given by equation 8, that is RL of r when r tends to infinity. That means the asymptotic form r tends to infinity denotes asymptotic nature. Therefore, RL of r when r tends to infinity is AL into cos del L JL of kr minus sin del L into NL of kr. This equation reduces to JL of kr for field free case when del L equal to 0. This is perhaps the reason why cos del L and sin del L are associated with equation 8. Here in the field free case, the change in phase angle del L is equal to 0. Therefore, when V of r is equal to 0, del L equal to 0. If del L equal to 0, sin del L is equal to 0. Therefore, RL of r when r tends to infinity is AL into cos del L JL of kr. Therefore, the only admissible solution is JL of kr. We know that the asymptotic expansions for JL of kr and eta L of kr are given by these two equations, that is JL of kr when r tends to infinity is sin kr minus L pi by 2 divided by kr, and eta L of kr when r tends to infinity is minus cos kr minus L pi by 2 divided by kr. Substituting these two values in RL of r in the previous equation, we get RL of r when r tends to infinity is equal to AL into cos del L and here we substituted for JL of KR plus sin del L, and here we substituted for eta L of KR. Then here see this equation, which is in the form of cos A sin B plus sin A cos B. Therefore, you can write this as AL divided by KR into sin KR minus L pi by 2 plus delta L, that is sin cos A sin B plus sin A cos B is equal to sin A plus B. Therefore, RL of R is AL of KR into sin KR minus L pi by 2 plus del L. Then the equation 9 is obtained by replacing sin KR minus L pi by 2 plus del L as e power I KR minus L pi by 2 plus del L minus e power minus I KR minus L pi by 2 plus del L divided by 2i, that is sin theta is equal to e power I theta minus e power I theta divided by 2i. By making use of that, we get this equation 9. Now you have an expression for RL of R. This equation 9 is substituted in this equation. U of R comma theta is equal to summation over L I power L 2L plus 1 RL of R PL of cos theta, which is nothing but equation 7. As I said previously, this equation 9 is substituted for RL of R in equation 7. After substituting the equation 9 in equation 7, we get u of r theta is equal to 1 divided by 2i kr summation over L I power L 2L plus 1 a suffix L multiplied by u to the power of I KR minus L pi by 2 plus del L minus e power minus I KR minus L pi by 2 plus del L into PL of cos theta. This equation is now compared with equation 5, which we arrived by using the Rayleigh's expansion. That is, the equation 5 is u of r comma theta is equal to summation over L I power L 2L plus 1 multiplied by e power I KR minus L pi by 2 minus e power minus I KR minus L pi by 2 divided by 2i KR into PL of cos theta plus f of theta into e power I KR divided by R. Comparing these two equations and equating the coefficient of e power minus KR on both sides, we will get a suffix L is equal to e power I del L. Similarly, equating the coefficient of e power plus I KR in above two equation, we will get this equation. That is, the coefficient of e power plus I KR of the first equation is 1 by 2i KR summation over L I power L 2L plus 1 AL Here this AL is replaced by e power I del L, hence here e power I del L. Then e power minus I L pi by 2 and e power I del L multiplied by PL of cos theta. This is this one, that is the left hand side of this equation. The right hand side of the equation is the coefficient of e power plus ikr of this equation. Here in this equation the coefficient of e power ikr are summation over L. Remember that this 2 ikr is taken outside the summation, therefore 1 divided by 2 ikr summation over L I power L 2L plus 1, and here the coefficient of e power ikr is nothing but here in this term e power minus L pi by 2 and then PL of cos theta. In the second term the coefficient of e power ikr is nothing but f of theta divided by r. Therefore f of theta divided by r. Here in this equation e power minus I L pi by 2 is equal to I power minus L. Therefore this cancels with I power L. Therefore these two terms cancel. Similarly in the right hand side also I power L cancels with e power minus I L pi by 2.
After cancelling and rearranging, we can get an expression for f of theta. Here the f of theta is equal to 1 divided by 2ik summation over L 2L plus 1 into PL of cos theta into e power 2I del L minus 1. In this expression, for this e power 2I del L minus 1 is written as e power I del L into e power I del L minus e power minus I del L. Then in the next equation e power I del L minus e power minus I del L is replaced by 2I sin del L. Here this 2I and this 2I gets cancelled. Therefore f of theta is equal to 1 divided by k summation over L 2L plus 1 PL of cos theta e power I del L sin del L. Here this is the expression for scattering amplitude f of theta. Then from the previous knowledge you may all very familiar with the expression for total scattering cross section. The total scattering cross section sigma is equal to 2 pi into integral 0 to pi f of theta the whole square sin theta d theta. This is equation number 11. In this equation 11, let us substitute for f of theta from equation 10. We know that sigma is equal to 2 pi by k square integral over the limits 0 to pi f of theta the whole square sin theta d theta. Here we are substituting for f of theta the whole square. F of theta the whole square or mod f of theta the whole square is nothing but f of theta into f of theta. One f of theta is in terms of L. For another f of theta we are writing in terms of L prime. Therefore sigma is equal to 2 pi by k square integral over the limits 0 to pi summation over L prime 2L plus 1 2L dash plus 1 PL of cos theta PL dash of cos theta into sin del L sin L dash into sin theta d theta. Taking out all the L's outside the integrals including the summation over L and L dash and retaining thetas inside the integral, then you will get like this. Then from the orthogonality theorem of Legendre polynomial, the value of the integral is equal to 2 divided by 2L plus 1 into delta L dash. Therefore this integral is equal to 2 divided by 2L plus 1 del L dash. Now when L is equal to L dash, this sigma is equal to 2 pi by k square summation over L 2L plus 1 the whole square. Then this is equal to sin squared del L 2 divided by 2L plus 1, because when L is equal to L dash, del L dash is equal to 1. This is the expression for total scattering cross section, that is equal to 4 pi by k square summation over L 2L plus 1 sin square del L. Let us now see the special case. We know that f of theta is equal to 1 by k summation over L 2L plus 1 PL of cos theta e power I del L sin del L, which we derived already. And then here e power I del L is written as cos del L plus I sin del L, and find out the imaginary part of f of theta from above equation, which is nothing but the coefficient of I, that is equal to 1 by k summation over L 2L plus 1 PL of cos theta sin square del L. Here this PL of cos theta is equal to 1, the value of which is, therefore the imaginary part of f of theta is equal to 1 by k summation over L 2L plus 1 sin squared del L, because PL of cos theta is equal to 1. Now if you substitute this value of imaginary part of f of theta in the expression for total scattering cross section, you will get the total scattering cross section sigma is equal to 4 by k imaginary part of f of theta. This expression for total scattering cross section is called optical theorem. Therefore this is called optical theorem in the case of partial wave analysis.